Hello, everyone. We want to spend some time today talking about pendulum motion, which was the source of most of what Julius Sumner Miller had to say. So you start with a rigid, like a ceiling or something that's not going to yield. You then have a length of string, and I'm going to color the bob. And that was the word that Julius had used. So in the language, this is called bob. We tried other names like Mike, Adam, Joe. None of them seemed to work, but Bob stuck. And the important thing about Bob is you're just going to have a mass. And as Julius pointed out, this string has a length from the ceiling to the center of mass of Bob. And it is a physics string, so that it has none of the characteristics that would get in our way, such as being able to stretch, rotate, having mass, anything like that. So it just exists to be what it is. Okay. So this system is described by the mass of the bob and the length of the string. So I'm going to move my L to this side so that we can do what our buddy Julius did. We're going to pull Bob to the side. Now, this is exactly the kind of thing you can do at home. It's just finding a mass that's on a string. I managed to make one with a pair of earbuds and the connector for them. But anyway. So we pull it to the side, some angle theta. So let's do the math that Julius was so carefully avoiding. And it's not that bad. First, I'm going to find my axis as the tip of the rotation point. Then I'm going to sum of the torques about that axis, and that's dl dt. And I'm going to do this with spin alone. And you'll recall that spin is equal to I omega. All right. So we build the free body diagram. There's the axis. We come down. And there's the mass. Okay. So let's see. For forces, we're going to have the force of tension. I hate that crayon. We're going to have the force of tension that's in the string. And are we done? I mean, it's got the string in it. You guys are too good for me. We're going to wind up with the weight. So the force of gravity acting on the pendulum. Okay. Now for a bit of geometry. We had this angle theta. And the motion of the pendulum is going to be instantaneously along the x-axis, and the y-axis is right along L. Okay. So that's theta up in this corner. Then this corner here with the crayon is phi. Now look at the y-axis anew. And I have to have a 90-degree angle here. So at the point of the mass, I've got to get to 180 degrees, which means this angle here has to be theta. And that's the one we need above all else, is knowing that angle between L and the force of gravity. So let's get rid of the work we had to do, since we know what theta is. We are looking for the component of gravity that will provide a torque. So I need F, the force of gravity, on the x-axis. And if that's theta, then that'll bring theta up to here. And we wind up with two possible torques. We had the force of tension, and we have now the force of gravity. So the force of the tension is, oh, that was a little sloppy. I can see you at home going, what the hell is that word? This is cross. So the force of my tension is directly along the length. Don't forget that torque is defined as R cross F. so that the cross product here is 0 because it's basically y cross y. The force of gravity then is the perpendicular component. So it's real, and its torque is going to come at us as L, the force of gravity, and the side opposite theta, which is sine. Okay, so let's get back to the dynamics. I can sum all of my torques, and it has to equal I alpha. So I'm going to plug in L, the force of gravity, which is just mg, and sine theta. And that's going to equal the I for a simple pendulum, which is a mass at the end of a spring. So it's a mass extended away from the axis point. So it's just going to be the mass of Bob and how far away it is. And then importantly for simple harmonic motion, alpha is the second derivative of theta with respect to time. Okay, cancel things out that are similar on both sides. And we get this relationship of G over L is going to equal, sine theta needs to be in there, d theta squared dt. This equation no analytic. You can't solve this problem with mathematics. You can plug it into a computer and it'll solve it for you, but it's only doing small iterations. So it's time for us to talk about physicists' favorite trick, which is the small angle approximation. And here's the goal of the small angle approximation. If you go to the geometric series that defines both sine and cosine, you find that the series are, for sine, it starts off with a and then plus I'm pausing to see if it's actually in our textbook, because that would just be sweet. Nope, they don't have it laid out easily. So this is as I recall, this goes a cubed over 3 factorial and so on. And this is 1 plus a squared over 2 factorial. And now that I'm thinking about it, I think the pluses and minuses oscillate. But none of that matters, because what we're going to ask is, I'm going to let this value of a be a lot smaller than we'd get with, so that's smaller than, yeah. And if we make this approximation, then anything that is raised to a power now really is not only just small, but now small. And this is the small angle approximation, because this allows sine of a to approximate a, and the cosine of a approximates 1. So with the small angle approximation, we can come back to our solution process and see that I'm going to wind up with theta g over L is equal to the second derivative of theta with respect to time. So our next step then is to make a guess at the solution of theta. And since we're in simple harmonic motion, a reasonable guess for the solution to this equation is going to be the same one we've been using before. How about a sine omega t? All right, so let's take our derivatives. Derivative of theta with respect to t. We know this as the angular speed omega, but we need to keep this angular speed separate from the omega in the equation, or all hell breaks loose. So I'm just going to call it v theta for now. And sine is cosine, so I get a derivative of sine gives cosine omega t, and then I have to reach inside the function to pull out the derivative there. We do this one, and we get the acceleration of the system going back and forth, so it's very non-constant. And we get minus a cosine, we get a sine omega t, and we're going to get omega squared out of this. So notice the minus sign has shown up again, which means we have to go back up and take a look at what's physically happening with this torque. This torque found up here is always pulling the it's always pulling Bob towards the center. So if you take a mirror image of this, you'll see the same thing, that the torque is pulling Bob towards the center. As the torque gets larger, which happens at larger angles, the acceleration is going to be there to, well, the torque is defined by how the acceleration is changing. So the direction of the torque is going to be defined that way. And that means we need a minus sign in here. We can put it over there if we'd like, since it's kind of looking forward to figure out why the minus sign is there. Okay, so now we do the same thing we have done before, which is you take your get the blue crayon out. We take theta as a function of t, put it in there, take the acceleration term, put it in this side of the equation, and we check to see how it's turned out. So we get theta as a function of time, which is now involved with our guess, is a sine omega t, and then there's that g over L. Let me put the minus sign here so we can cancel it out. Then we have just the acceleration, which was minus a sine omega t omega squared. So we cancel out what we can. This goes away. The whole a sine omega t goes away. And we wind up with our equation for the angular frequency of the motion, which says omega squared has to equal g over L. So let's spend just a moment here, because I want to get omega squared, which we just solved was g over L, for this to jive with what Julius Sumner Miller had written on his incredible flying paper board. So omega is equal to g over L, and square rooted, and omega is also equal to 2 pi over the period. The period again is defined as the full motion of the pendulum. So where it starts, it has to get back to that point going in the correct direction. We combine these together. There's 2 pi over t, g over L. So our period, just flip everything, is going to be multiply both sides by 2 pi. And this was the expression that he had given to us. So what Julius Sumner Miller said was impossible to derive is within our grasp. We also need to then, so this is how a pendulum swings. So as you watch it over time, you get an amplitude, which is as far as theta is going to go, so we'll call it theta max. And then sine omega square root of g over L multiplied by time, and this will describe how a pendulum swings. So as Julius pointed out, it's not dependent upon the mass at all. This motion depends upon the local gravitational field strength, G, and L, the length of the pendulum. Okay, so everything we've done here can be derived in the specialized case of anchoring a physical pendulum. And by a physical pendulum, what I'm saying is we can't reduce it simply to its mass. But everything we've done is familiar once we choose the center of mass, because that's where the force of gravity is going to act. The tension is all internal to the rod, and it's zero anyways as far as it comes to a torque. So you solve this physical pendulum problem the same way we did the simple pendulum above. So the physical pendulum is just sum of the torques is equal to I alpha. Only you can't decompose you can't decompose I. I is given by the shape of the object. So if you do it, you can solve for the physical pendulum now using the exact procedures we did above, and see if Julius Sumner Miller was right about the values he got for the physical pendulum. And I'll revisit this physical pendulum in an example soon.